Remember, the general notation for an n by m system looks like this, and it's quite messy with lots of symbols. Turns out that we can write an n by m system much more conveniently using matrices. For example, let's say I have a 2 by 2 system like this. I create a 2 by 2 matrix called A containing all the coefficients in front of the x's in the system. So the A matrix should be 2 by 2 as well. The element in row 1, column 1 should be the coefficient in front of x1 in the first equation. And there is a 1 in front of x1 in the first equation. First row, second column, the coefficient in front of x2 in the first equation, and there is a 1 in front of x2. Second row, do the same thing but for the second equation. So there's a -1 in front of x1 and there's a 1 in front of x2. This will be called the coefficient matrix of the system. Then I create a column vector x containing all the x variables, and there are 2 x variables in this case, and I stack them on top of each other like this. And finally I create a column vector of the coefficients on the right hand side of the system, which I'm going to call b. So b is 2 by 1 containing the 2 from the first equation and 0 from the second equation. Using this notation, this equation system right here, this 2 by 2 system, can be equivalently written as A times x is equal to b. These are 2 equivalent ways of writing exactly the same thing. So let's double check that these notations mean the same thing. First, here I have multiplication. It's matrix multiplication. Whenever you have matrix multiplication, make sure that multiplication is allowed. So this A is 2 by 2 and the x is 2 by 1. These are the same, so I know matrix multiplication is allowed, and I know that A times x is 2 by 1, which is precisely what b is. So it does make sense. So I can do matrix multiplication and the equality is defined. Next, let's check what A times x is. To do the matrix multiplication A times x, let's write A here, and we write x to the right and above here. And the result we write here, which I know must be 2 by 1. To find the element in row 1, we do the dot product of the first row with the first and only column, and that's given by 1 times x1 plus 1 times x2, or simply x1 plus x2. To do the second row, we do the dot product of the second row with, again, the same column, and that will give us minus x1 plus x2. So what we see from this exercise is that when I do A times x, this matrix here, A times x, will contain the left-hand side of the equation system. First equation in the first row, and so on. And since b here is simply equal to the right-hand side of the equation system, saying that ax equal to b is precisely the same thing as the original systems of equations. Remember that equality sign in a matrix relation means that each element of the matrices to the left and to the right of the equal sign must be the same. That means that the first row of AX must be equal to the first row of B, and that is precisely the first equation. So in general, if I have an n by m system, n equations, m unknowns, then I define the coefficient matrix of this system simply as the matrix A, which is n by m, containing all the numbers in front of the x variables on the right hand side. Then, once I have the coefficient matrix of an n by m system, I define x and the b column vectors. X will be the column vector of all the x variables. So the matrix A is typically a matrix of constants. The vector x is a vector of variables. And I define a vector B which contains the coefficients, the constants on the right hand side of the equation. As this is an n by m system, I have m unknown variables, which means that x must contain m x variables, and it must be m by 1. I have n equations, which means that I have precisely n constants on the right hand side, so b must be n by 1. And you should convince yourself that if you do a times x, you get precisely what's on the left hand side of the system of equations. A times x will be n by 1, and the first row of a times x will contain the left hand side of the first equation, and so on. That simply follows from doing the dot product of the first row of A with the x vector. So the entire system can be written as AX equal to B, which saves a lot of notation. Let's remind ourselves of a few basic facts about equations. If I have an equation such as 2x equal to 4, I can solve this equation simply by multiplying both sides by a half, or if you like, divide both sides by 2, and I get x is equal to 2. We know that it's always allowed to multiply both sides of an equation with a constant as long as this constant is not 0. That will in no way change the solution to the equation. Another thing we can do to equations is if I have an equation like this, x plus 2 equal to 4, I can add minus 2 to both sides of the equations. Or if you like, subtract 2 from both sides, and I get x is equal to 2. And we also know that you can add any number to both sides of the equation, and that will not change the solution. And in this case, there are no exceptions, like the exception of 0 in the first case. So these are the two fundamental operations that are allowed on equations which we use to solve an equation. If I have a system of equations, then the fundamental operations are still available. So I can multiply both sides of each equation by any number as long as it's not 0, and I can add any number to both sides of these equations. And for systems of equations, I have a third fundamental operation. I can interchange the equations. That's not going to change anything. So if I simply take the first equation and put it right after like this, that's not going to change the system. So these are the three fundamental operations that you're allowed to do on systems of equations. You can interchange or swap any two equations. You can multiply both sides of an equation by a non-zero constant. And you can add a constant to both sides of an equation. The third one is particularly useful for solving systems. Let's take a look at this simple 2x2 system again. By simple inspection, we can see that x1 equal to 1 and x2 equal to 1 will be the only solution. We can also draw these equations. I've just renamed x1 to x and x2 to y, and the equations look like this, where we see that 1, 1 solves both equations. Now the third operation is the most useful one for solving equations. The third being that you can add any number to both sides of an equation. Let's take a look at the second equation. x1 plus x2 is equal to 2. And let's add 0 to both sides of the equation. If x1 and x2 is a solution to this system, then I know that minus x1 plus x2 must be equal to 0. So I can simply replace this 0 with minus x1 plus x2. That will not change the solutions. If I simplify this, I have on the left hand side 2x2 and on the right hand side I have 2. So I have now transformed the second equation into a much simpler equation involving only one unknown variable, which is simple to solve. The solution is x2 equal to 1. So instead I have two equations. I have my first one, and my second one now reads 2x2 equal to 2. So I have two systems and they must have the same solution. If x1 and x2 is a solution to the first, then I have done nothing to the second by adding 0 to both hand sides. And so x1 and x2 must be a solution to the second as well. But keep in mind that they are not the same equations. Here is a graph of the equations in the second system, but the solution has not changed. And once I've transformed the system into the second one, it's now very simple to solve. Once I know that x2 is 1, I can use that in my first equation to conclude that x1 must be 1 as well. So we use this trick to eliminate x1 in the second equation. For example, let's say I have this system. Now simply adding the first equation to the second won't do anything for me. But if I multiply the first equation by minus 3, I have minus 3x1 minus 3x2 equal to minus 3. Again, we know that that's allowed, won't change anything. If I now add it to the second equation, plus 4x2 equal to 4. If I add these together, the x1 cancels and I'm left with x2 equal to 1. And my new system reads x1 plus x2 equal to 1 and x2 equal to 1, which has a simple solution. x1 is 0 and x2 is 1. So let's summarize this. Let's say that I have an n by m system of linear equations, ax equal to b. Then I have three elementary row operations available for me. The first one is that I can interchange two equations. That's called a swap. The second one is that I can multiply an equation by a number which is non-zero. That's called a scale. And the third one is that I can add any number to both sides of an equation. But we rephrase this slightly to make it more useful. We say that we can add to one equation a multiple of another equation. And we replace the equation by the sum of this. What we have concluded is that if you perform an elementary row operation on a system, any of these three, we know that you will not change the solution set. Your new system, once you've performed an elementary row operation, will have exactly the same solution or solutions as the one you started with. So this is so useful that we have some terminology for this. We say that two such systems are equivalent if they have the same solution set. Performing an elementary row operation on a system will give you a new equivalent system. Let's take a look at this system again. The way to solve it is to add the first equation to the second. That gives us minus x1 plus x2 is 0. 2x2 is equal to 2. Then I multiply the second equation by 1/2. which gives me minus x1 plus x2 is 0, x2 is equal to 1. In the next step, I add minus 1 times the second equation to the first. That gives me minus x1 plus x2 minus x2, that's 0. 0 minus 1, which is minus 1. And the second one is x2 equal to 1. And in the final step, I multiply the first equation by minus 1. And that tells me that x1 is 1 and x2 is 1. Now, I can save a lot of typing by doing the following. I begin by writing down the coefficient matrix. That's minus 1, 1, 1, 1. To the right of the coefficient matrix, I put the b vector, the vector of constants for the right-hand side of the equation. So that would be 0, 2. This matrix is called the augmented matrix of the system, and it contains all the information in the system. And basically, it has A followed by the B vector. Then, instead of solving the system, which I do on the left-hand side, I can work with this augmented matrix. So I add the first row to the second of this augmented matrix. That gives me minus 1, 1, 0, 0, 2, 2. That's an elementary row operation on the matrix, corresponding to the elementary row operation of the system. And this second matrix contains the same information as the second system. I move on, multiplying the second row of this matrix by a half. That's minus 1, 1, 0, 0, 1, 1. I add minus 1 times the second row to the first. That's minus 1, 0, minus 1, 0, 1, 1. And in the final step, I multiply the first row by minus 1, 1, 0, 1, 0, 1, 1. The matrix is now in reduced row echelon form. And in this form, it's trivial to see what the solution is, 1 and 1. We see that the three elementary row operations on a system of equations, they correspond to the same elementary row operations on matrices that we have discussed before. And I know that if I perform an elementary row operation on a system, I get a new equivalent system. That in turn means that if I perform an elementary row operation on an augmented matrix, I get a new augmented matrix which represents a completely equivalent system. To summarize, we define the augmented matrix of a system. The augmented matrix of the system AX equal to B is a matrix that we call C. It has dimension n by m plus 1, consisting of first the matrix A, the coefficient matrix, and to the right of that we put the vector B. That's why the dimension becomes n by m plus 1, because A will be n by m, then we add one more column, making it n by m plus 1. It saves us a lot of notation working with this augmented matrix instead of working with the system, but more importantly, we can use results from matrix algebra to conclude important results for linear systems by considering this augmented matrix. So the basic principle is then this. Instead of working with this system AX equal to B and do elementary row operations on this system to make it simpler such that we can deduce what the solution is, we perform elementary row operations on this augmented matrix C instead. And as we shall discuss in the next lecture, The basic idea is to perform elementary row operations on this matrix C, the augmented matrix, such that it will be in reduced row echelon form. Once C is in reduced row echelon form, it's very simple to deduce what the solution to the system is.